Hello, everyone. My name is Rolando Garcia, and I'm a fifth-year PhD student at UC Berkeley. Today, I'll be talking to you about one of our latest pieces of work, Hindsight logging for model training. So when data scientists log in machine learning, they're logging a lot of data. They are logging time series, tensor histograms at high frequency, and images and overlays as they change over time. And there's a very simple reason for why the data scientists are logging all of this data. Primarily, it helps them diagnose errors in the model as it trains. Errors like dead ReLU problems, exploding or vanishing gradients, reward hacking, and so on. Consequently, it doesn't come to me as a surprise that big players like Google have a TensorBoard offering as well as Databricks' MLflow, but there's new startups that are arising in this space, such as Weights and Biases, which recently raised like 45 million in its latest round of funding. So now that we all have a common understanding about what I mean by logging in the space of model training, I'll talk about our actual technique, which is hindsight logging. And instead of just telling you what hindsight logging is, I'd prefer to show you. And I'll show you by introducing you to my friend Chuck. Chuck is a first-year PhD student in astronomy who likes to try the latest and greatest models from arXiv. He also knows how to implement them himself. Chuck trains his models in the cloud using interactive notebooks that are served by his lab administrators. Next, we will walk through Chuck's workflow with a special emphasis on how he logs additional training data. So on the first step, Chuck is going to train his model in an interactive notebook that is served in the cloud. This cloud-hosted notebook is going to have access to a GPU, and so he trains the model. Then, as the model trains, he's going to collect and monitor some basic training metrics, like the accuracy or the recall of the model. In most cases, this information will be sufficient, and Chuck will either drop the model that he's training, try other alternatives, or declare success. But every once in a while, the anomalies that Chuck will notice in the accuracy may be signals or indicators of a bigger problem. And so in this case, he may need to step back in and drill down or add additional logging statements. Once Chuck has finished adding those logging statements to his code, he will re-execute. And when training re-execution finishes, he will have access to that additional training data, which in this case is just the tensor histograms as they change over time. In Chuck's workflow, there is going to be 2 complete re-executions of model training. And what I find the most astonishing about this workflow is the fact that the re-execution takes as long to complete as the first execution. This strikes me as unusual and also very extreme. Now, what if I told you that there's a technique for reducing the re-execution time from 7 hours to 2 minutes? Would you be interested? Here you are seeing a 2-axis plot for the replay time for ResNet 152 on CIFAR 100 ran for 200 epochs. So far we just have one data point. It's one instance with one GPU running the experiment. The y-axis on the left plots the replay time, and the y-axis on the right plots the cost. In this case, we see that it takes approximately 400 minutes, or close to 7 hours, and the cost using an EC2 machine is $20.20. Now, look at what would happen if Chuck were to re-execute with additional GPUs. In this case, he'd be using another EC2 instance with 4 GPUs. The cost stays approximately the same, but the replay time is cut significantly. This trend would continue as Chuck were to add additional GPUs. And note on the far 2 histograms that the GPUs do not even have to be on the same machine. They can be on completely different instances. The reason why such dramatic speedups are possible without increasing the net cost or resource consumption is due to parallelism. The rest of my talk, as well as our paper, can be summarized by this slide. Model training replay is embarrassingly parallel given periodic checkpoints. In this slide, I'm showing you an abstract example of model training, as it would be written in modern frameworks such as PyTorch or the newer versions of TensorFlow. There are SGD steps that are taken once per batch of training data, and the whole process is repeated for multiple epochs. Additionally, state is checkpointed at a frequency of about once every epoch. At a lower level, this workload is a sequence of stochastic gradient descent steps with some intermittent checkpointing. We can kind of think of this as a transaction consisting of reads and writes, and that's how we can start to think about possible ways of parallelizing the replay of this workload. Now, at replay time, think about how the second GPU would set itself to the correct starting state. One option would be to execute every instruction before its starting point, but another option is for it to just load the checkpoint and set itself to the correct state. In other words, checkpoints break dependencies between the multiple workers, and so they're able to execute independently, and they're able to complete without communicating or coordinating. They never wait. In the paper, we discuss in more detail our mechanism for auto-parallelizing the replay of model training. Last, I'm going to share with you a few technical details about how we do periodic checkpointing in order to enable efficient replay. Because serialization is time-consuming and Python is a single-threaded language, we want to do everything that we can to make sure that serialization is happening in the background. Our mechanism leverages fork for copy on write semantics to avoid serialization on the main thread. The forked or child process is then dedicated to serialization and I/O, while the main process can continue to do productive training work. In this plot, I am showing you the same model training execution and one that does relatively heavyweight logging. That is, plotting the tensor histograms 4 times per epoch. On the left side, we see the overhead or the total runtime that the workload would take when logging is performed synchronously. The purple histogram on the right does the same work, but it does so asynchronously. Our background logger cuts overhead due to serialization, reducing net record overhead by 74% on average. Earlier I told you about my friend Chuck, who is a first-year PhD student in astronomy. He is a domain expert, but a non-technical user. We just saw how important checkpoints are for enabling parallel replay. As a result, they seem too important to make them the responsibility of the model developer, especially when more and more model developers are increasingly non-technical domain experts. In the paper, we present techniques that perform static analysis for side effect estimation and allow us to instrument model developer code to automatically record and take periodic checkpoints. So let's recap by taking a look at Chuck's improved workflow, one where Chuck performs auto-record and auto-replay. He would still train the model as he used to, and because the record imposes very low overhead, it would still take him just as long to train. In the extraordinary case where the laws indicate some kind of anomaly that required digging down further, he would add more logging statements or Hindsight logging statements and would replay. And at replay time, the auto-record feature would parallelize by leveraging the existing checkpoints taken at record time, so that the replay time would take 2 minutes, down from 7 hours. We have open sourced the system that we present in the paper, and it's available at ucb-rise/flor. That is all. Thank you very much for your time and attention. I hope to see you later at the poster.